Hello, and welcome to the first topic of Chapter 5 of our textbook on integration. And the topic of this section is Antiderivatives and Indefinite Integration. Okay, so we'll dive straight in by considering this. It's a very sort of kind of small differential equation. Okay, so assume we know that y prime equals 2x. In other words, the derivative of y is 2x. Well, what is y? Okay, what is y if y prime equals 2x? Well, what we're saying is, what is the thing that differentiates to 2x? Okay, well, we know enough about that we probably have a reasonable guess that maybe that's x squared. Right? If y is x squared, then its derivative is 2x. And maybe we're happy, but then we can ask, well, what about that? What about x squared plus 1? What's the derivative of that? Well, that's also 2x. And then you start thinking, well, maybe we can just keep going. We could add 8.3, or we could add pi, or we could really add anything we want as long as it's a constant. And in fact, we literally would go on forever. There are infinitely many possibilities here. Okay, and all of these y's differentiate to 2x, kind of like a family. Okay, so here's our definition. An antiderivative of small f of x is a function big F of x such that big F prime equals small f. Okay, so that's an antiderivative. Notice we saw on the previous page that there were several possibilities. And then the set of all antiderivatives, so all the possibilities of f of x, is the indefinite integral, and it's denoted here by this symbol here. Okay, and we'll talk about that. But we say this as the integral of f of x dx. Okay, and just thinking about what all of those antiderivatives must be, remember we had the big F, and we could add whatever we wanted to it as long as it was a constant, so we'll call it big F of x plus c for some constant c. That's the family of all the antiderivatives. Okay, so we mentioned this integral symbol here. Okay, and let's have a little look at this. Okay, so just looking here, so this is the integration symbol. Okay, it looks slightly like an elongated S. Okay. This piece here, the function we have in here is called the integrand. Okay, that's the thing we're integrating. And then the dx, well, that's the differential of x. That tells us what we're integrating with respect to. Okay, when we start these integrals, it'll probably be fairly straightforward that we'll just have maybe just a function of x and the differential of x. But as we're moving through these topics, and particularly we start doing things like substitutions, it'll be important what goes there. The big F of x is just one antiderivative. Okay, something we can find that differentiates to small f of x. And then we add in this c, this constant of integration. Okay, and that takes care of the fact that we have all these different possibilities with these constants added. Okay, so that's our first look at indefinite integration. Okay, so let's suppose we want to find some antiderivatives. So let's take a simple example. Suppose we want to integrate cosine x dx. So in other words, what differentiates to give cosine? There we go. And so that would be big F of x is sine x plus c. Okay, sine x differentiates to cosine. Of course, we have the constant of integration, the c, every time. Still the same thing here, which is not so bad, but there's three different pieces now. So let's look at each piece in turn. So if we integrate e to the x, well, we know that e to the x differentiates to e to the x, so we know that e to the x integrates to e to the x. And we can add a constant. I'm just calling this c1 right now because we're going to see a couple of possibilities. 6x would be 3x squared plus a c2. And then the 7 would be 7x plus c3. And so we want to integrate all of those pieces, and we'll see the formal rule of how we can do this in a second, but we can just take each of those and add them together. But notice here we now have three constants of integration. If we're just talking about constants, we may as well combine them all together. So we can sort of say that the c we have here is just c1 plus c2 plus c3. Okay, and then this is therefore our integral or antiderivative. And notice throughout everything we're doing today, everything we've done so far and we'll keep doing, we can always check if we've done this correctly by simply differentiating back again. Okay, the whole point of this integral was that if we differentiate it, we get back to where we started. And so we can always check that if we differentiate, we get back to the original, and sure enough, that is the case here. Okay, so here's some rules, and in the left-hand side, you'll see we have the differentiation rules, which hopefully are pretty familiar. On the right-hand side, they're the indefinite integral rules we can sort of take from that. And so you can see they all kind of pair up. So for example, the very top one here says if we have a constant multiplied by it, we can take the constant out, and we can do the same on the right hand side here when we're integrating. Number 2 is the rule we just used. If we have two functions added together or subtracted, we can integrate them separately and simply add what we get. The integral of 0 is c, because if we differentiate the constant c, we'd get 0. We have the power rule here. This is an important one. Okay, we call the power rule for differentiation. We bring the power to the front and take one away from the power. For integration, we add one to the power, then divide by that new power. Okay, so here we get the integral of x to the n is x to the n plus 1, and then we divide it by the n plus 1. Notice just one other thing that doesn't work for n equals negative 1, because we get the 0 there. Then we have a couple of the trig ones at the bottom there. There's a few more here, a bit less common. Okay, but over time, as you get practice, these will become more and more familiar. Okay, and we'll just finish off with an initial value problem. We've seen that we can actually get a whole family of solutions. These initial value problems actually kind of fix that c. They give us a specific solution. So for example, suppose f prime of x is 5 e to the x, and we know that f0 is 10. Well, if we want to integrate to get just f of x, if we know f prime, so we're going to integrate 5 e to the x dx. Okay, and in fact we know, because e to the x is such a simple integral, it just goes to e to the x. Also, we can leave the 5 outside. Remember, that was one of our rules we just saw. But we also have the plus c. Let's say now we can use this initial value we were given to find the c. So we know that f of 0 equals 10. We can just plug in the 0 for x, and it should equal 10. So we get 5 e to the 0 plus c equals 10. Of course, we're going to solve that for c, which gives us c equals 5. Remember, e to the 0 is 1. So that gives us c equals 5. So in fact, we get that the solution now, rather than the family of solutions, the solution here is f of x equals 5 e to the x plus 5. And that's about it.